Okay, good evening, everybody. Welcome to the fall lecture series of IAAC. Today we are really happy to have with us Kai Strehlke. Kai is a good friend. We actually met him back in 2015 when we started working in the project of InnoChain that connected a series of academic partners with industry partners on research related to combine digital technologies with new material systems and new constructions, let's say. And it was it was always great because Kai is a very active member of both the academic community as well as the practice and the industry. And he is basically the head of CAD and CAM in the Blumer Lehmann company. It's actually the leading timber construction company in Switzerland. And Kai is the mind behind CAD, CAM, and behind all the digital technologies related to CNC manufacturing and digital data, and of course, with the goal to produce large-scale timber structures. And he has been also working in different other practices besides the academy. He has been at Herzog and de Meuron for some years. He has developed there the Department of Digital Technologies, but he also, as I was saying, taught design and digital processes at the Bern University of Applied Sciences in the Department of Architecture. So today, Kai will share with us Freeform timber construction strategies and tricks, and the complexity, the challenges and the opportunities of working with timber and freeform geometries. I guess he will present a series of different projects, including the exceptional Cambridge Mosque, Kai, by Marks Barfield Architects. But besides that, I think you will be sharing with us a series of other projects that, as I was saying, challenge the possibilities of using timber in geometries that we have never imagined before, no? And at a moment that we are more aware than ever about the impact of the construction industry and the materials that we're using for our construction, I think that revisiting the possibilities of timber into the architectural construction and understanding that the scale is not limited or the forms are not limited, I think that this is a very important moment to share the work. You know that from IAAC side, we are in love with wood and timber, and we are experimenting a lot with natural materials, including earth. And of course, timber. And I think that our community of students and faculty, but also the people that are joining us here today, really looking forward to watch your talk, but also to discuss with you after that. So Kai, thank you very much for accepting being with us. And please, the floor is yours. You can start sharing the screen.
So thank you. Thank you very much for inviting me for the introduction. I will start sharing the screen. Should work now, huh?
Yeah, it works perfectly.
Perfect. Okay. So I will talk about freeform timber projects. I will do a short presentation of the company of Blumer Lehmann, a company I'm working now, I think, 6 years with. Then I will present the project you see in the background, which is the Cambridge Mosque, which, to my opinion, is one of the most beautiful projects I've ever worked on. And I had the chance to be part of the team working on that project. I will also present some work we are doing together with universities on a research level. And if I have time in the end, I will show some teaching projects I've been doing before going to Blumer Lehmann, but I'm also doing now together with Blumer Lehmann and some universities. So, oops. Blumer Lehmann is an old company of 147 years. And what is super amazing to me is you can see the green, not forest, but the trees here. You have a very, very little creek. In this creek, you have nearly no water. And to me, it's a fascinating thing to imagine that 147 years with this very, very little water, somebody came to the idea to create a sawmill. And that out of this sawmill in 147 years, there is a very big industrial village which is standing there now. We are dedicated to the value chain of wood. So we take the wood within something like 90 kilometers. We have our own sawmill and we produce lumber for construction, for silos. We also sell them on the market, or we use the chips and create pallets and briquettes with the bark of the wood. And what we cannot use, we burn it and we create enough energy for all the machines on our campus. Or we create, I think, electricity for 6,000 homes with what we burn in our company with the leftovers. So we really close the circle of wood. The company itself is it's a family company by the family of Lehmann. Katharina Lehmann is the president of the Lehmann Group, and she's representing the company in the 5th generation. And I said the company has 147 years of tradition. I think Katharina is really the figure in the company who is able to look back these 147 years and really worship the tradition of working with wood and the history of the company. And she's also interested to see where the wood is going in the next, let's say, also 147 years. So she's very interested in working with universities, and she's also extremely dedicated on doing research on wood and on the fiber of wood. The portfolio of the company, so we produce different kinds of buildings. This building here is a housing building. I find it quite interesting because when I studied architecture some 30 years ago, we were not able to think about wooden buildings which are taller than 2 stories in Switzerland because of the fire regulations. So when I studied architecture, wood was clearly to create chalets or family houses, 2-story buildings, nothing more. And the fire regulations changed dramatically in the last 15 years. And I think this gave this big impulse what is nowadays possible to be done in wood. Here is an example of the hotel industry. It's quite interesting because some parts is modular building, some parts is a system building, and it's a mixture of these different strategies of construction we used here in this building. That's a building done with Herzog and Dummerow on a mountain not very far from Gossau, the Käseruck. It's a beautiful place and a beautiful building. An example of industry and commerce, more and more done in wood. Before it was only done in steel, more or less. And this is quite an amazing building we've done together with Shigeru Ban in Zurich. It's a Tamedia building. That's the headquarters of a news group. And the interesting thing, it's like a 4-story, 5-story building in an urban context. And it's really waking up or taking advantage of all these new things of using wood inside a higher building in an urban context. And I think this building for Zurich, it's really one of the key buildings which is bringing the wood back in the kind of urban context. Another example is extensions and renovations. In Switzerland, we have a big topic is densification of cities. And if you densify a city, wood is an extremely valuable material because it's a light material and you can build on top of existing buildings, like you can do extensions, something you can not so easily do in concrete because you have to make stronger the fundamentations and the structure of the building very often. So wood is a light material and it's very easy to do extensions with it. And I think this will be a very big topic also in the near future. Another example, it's education modules. We have different strategies of building. One is doing modules. A module, we do these for schools in Zurich. And it's quite interesting because we can build a building like this within a week. So we can place 13 modules a day, and a building like this can be built in the holidays in school time. So that's quite a big advantage of using these modules in schools. And the second advantage is in Zurich, we have quite a big urban movement, like areas where a lot of new constructions are built and there are a lot of new families going there. And then the schools need much more place for some 10 years. And after 10 years, it's going down. You don't need so many space anymore in these areas. And we can like move these schools from one area to another one inside of the city. So Zurich is renting these schools and they are placing these schools wherever they need them in the city. That's Freeform building. It's a weekend house for, I think, 2 people, 1,600 square meters, done with Fosses and Partners. And what we've done is this freeform roof on top of the building in Turkey. So I will talk about the Cambridge Mosque, but I just want to say one thing, which I think it's a key point of the success we have in the company. You see here the phases in the architecture. In Switzerland, it's called SEA, in Germany, HOI. And normally a constructor is always getting into the game after the submission. And in freeform structures, complex architecture, this is much too late. And this is a very big problem in open buildings like the Elbphilharmonie in Germany, where a constructor was not allowed to be contacted before the submission. So we really, I think, we do a lot of pilots before the submission, and this is a kind of feasibility study. We already work on a 3D model. We have an initial analysis, and because of this pilot, the mock-up we are doing, we get a quite good cost estimate, and we really, the buildings stay inside of these costs. After the submission, if we are successful, we get into the project, we do the planning and the production, and very often we do the whole package until the assembly and the maintenance of the building. So very often we do not only do the production, but also the pre-assembly, the transport, and the final assembly on site. Everybody is talking about BIM. We work with 3D models. We very often work with Rhino, but it's not only a geometrical model, it's an informed model. It's, if you want, it's a building information model, but it's not a Revit model, not an IFC. And we use it already in the mock-up as a communication model between the architecture, the structural analysis, the engineers, and us, the production. And I don't want to go too deep into it. Between the architecture and us, we talk about qualities, interfaces, the quality of the wood finishes, things like this. Architecture and engineers, of course, the detailing and dimensions. And something which is quite important is between us, production, and the engineers, tolerances and junctions. You can imagine that an engineer would like to have a building with very, very little tolerances so that the forces are really flowing exactly like he's calculating it. And we are interested in having a building which we are still able to assemble. So we need tolerances. And this very often is quite a discussion between the engineer and us to discuss what kind of tolerances we need for a certain kind of building. Here you see 4 different kind of projects, which on a very first sight look alike. It's like tree structures, but you see they are quite different, all these kinds of trees. And I will talk about the Cambridge Mosque much more in depth. But if I'm just comparing these kind of trees, here it's a Grand Hall in Yochu. It's a structure which is only singly curved, like only the wood is much cheaper, much easier to produce. It's much easier to produce it on the machine because you always have a flat surface, and all the parts are assembled from a vertical point of view from the top. This is something done in the workshop by more or less by hand. And these 2 buildings here, they are quite the Formula 1 of wood construction. So it's a doubly curved surface, but the wood itself is also doubly curved. And the assembly is not done from a vertical point of view, but normal to the surface. And then you get very, very complex joints and a very complex assembly order to realize the building. So the mock-ups we are doing, it's super important also to discuss qualities like knots, the wood. When you look in the wood, this is a mock-up we've done for the Cambridge Mosque. And you can see here the lamellas are in one direction. And when you go up, you see that sometimes we have to turn the direction of the lamella because of the curvature of the beams. And you can also see that some lamellas are extremely thin, some are thicker, and then here we have lamellas of 40 millimeters. And this is something quite important to analyze in the beginning because this kind of wood is much more expensive than this one here. But I will go in depth more in the presentation of the project. So mock-up for us is a very important tool to support a design, to develop a design. We have architects like Norman Foster, for example. He comes very early. Very often he's working for 2 years on mock-ups, on samples, and he's taking all the knowledge he's taking out of these mock-ups and incorporates and changes his design with them. So it's a feasibility study. And one thing a mock-up is super important and helps a lot is we do complex buildings, and very often the decision makers have problems to take a decision, take all the money for the next stages. And a mock-up gives a lot of confidence into the project and helps a lot for fast passage through decisions. And it looks gorgeous. It's the first time you see the real building. So now I will make one presentation of the Cambridge Mosque, England, by Marks Barfield. The architectural concept behind it's a mosque was that Marks Barfield, they wanted to create a garden and have people pray in the garden. So they wanted to have a kind of place for people. It's the image they had. And they wanted to have these trees growing, and out of these trees create a kind of roof. And under the roof, in the shadow of this roof, having the prayer hall. That was one thought and one idea of the project. The second one, he didn't want to do a kind of mimicry of Arabic architecture. He didn't want to make these mokarabes you see in the Alhambra and in Arabic countries. So he wanted to create a mosque which has a connection to this kind of Christian architecture of the in England. So here he used this is also a vaulted roof in Cambridge. This is another vaulted roof. So he used this as a kind of inspiration idea. And at the same time, he worked together with a professor for Islamic art. and they worked on a kind of ornament, Islamic ornament, and they wanted to derive out of the ornament the kind of structure. So this ornament, you have this kind of octagon with a kind of positive figure and a negative, like this is the positive figure, and here you have the negative figure. And this is a symbol for, it's a pattern which is endless. So by being endless, it's representing God or Allah, and it's representing the rhythm of life with this breathing in and breathing out. And out of this kind of pattern, they created this, they changed this pattern to this geometry and used this for the structure of the building. So this is how the architects came to, with the geometry. You see the dimension are all like they're still changing. You also see that the geometry will change quite a lot during the project. And when I was working at Herzog & Dümmerow, I would have done exactly the same thing. I would have done a revolving surface and a flat surface here. And it's a kind of geometry which is very easy to do in Rhino. If you want to do this kind of master surface, which is optimized, it's already much more complicated to generate it in Rhino. But normally when you have a kink in the surface, very often this is a part where you want to have a connection later on also in the construction. Very often, if you have a connection here, you have to be sure that you get normal forces, because otherwise it's you get bending moments and bending moments here. So the first step, this was done together with design to production software company, very known in this kind of digital world in Zurich. So the first thing, they changed this geometry and created a kind of optimized master surface. I was talking before about BIM and IFC. Until when we were doing this project in IFC, you could not translate NURB surfaces. You could only translate meshes. And meshes are not producible, because if you have a mesh and you run it on the machine later on, you always have a tool which is normal, like you have in a triangulated surface, a lot of flat surfaces with small kinks. And you can imagine if a tool has to run over it, the tool will go in parallel onto the kink, and then there's a small rotation. And then it goes parallel with a small rotation. And even if this mesh is very, very fine, it will slow down dramatically the machine, and you will always see this kind of kinks. You will never get a very nice surface. If you have a NURB surface, you have a mathematical defined surface. So you have on each point on the surface, you have one normal direction. And if you have a tool running over this kind of surface, you will have a continuous flow and change of angles and everything, and you will get a much, much better quality in the production later on. So the steps we use to produce the project is the first thing. I talked about the master surface. I talked about the grid. We projected the grid into the master surface. The second step was together with the engineer to define the dimensions. What we have here, we have defined the dimension. What we don't have a segmentation. We don't know if all these are lots of very small parts which are connected together, or if this is one continuous beam here. And in the third step, we do an analysis of the curvature of these beams. And this is, I think, one of the key points and the most important point to really understand the project and get it in costs. Because what we need later, we need wood which is bent directly in the direction of the member. Because we can only pass forces into the wood along the fiber, not across to the fiber. So we have to bend, finally, we have to bend the wood exactly in this direction. And here we, here you can see, can you see, like in the top, I don't know if you can see it or if you also have this beam here. Oh, yeah. We have a curvature of 2 meters, and here we have some curvatures of something like 8 meters. And out of this curvature, oops, we can, just a second. Do you see this black bar in the middle here?
No, Kai, we cannot see your window. It's all fine with us. The
Perfect.
presentation is clean. Perfect.
Okay, so what we need to bend the wood, and you can imagine if I have if I take a piece of wood and I try to bend it, there's a moment where it will crack and break. So there is a relation between the bending of the wood, the curvature of the wood, and the thickness of the lamella. If these would be super thin lamellas, it would be very easy to bend them. If this is one big beam, it would crack. So there's a ratio about the smallest curvature divided by 200 gives us the thickness of the lamella. And if you imagine before, I was showing curvature of 8 meters. 8 meters divided by 200 gives us a thickness of 40 millimeters. And this is an industrial lamella. This is the cheapest curved wood you can get, because you normally in glulam, you always work with 40 millimeter lamellas. And if the radius gets down to 2 meters, divided by 200, you get a lamella thickness of 1 centimeter. And this is how we are producing the glulam. So this is singly curved beam. You see the lamellas. They have a maximum width of 28 millimeters. And then here you get the height of the lamella, or the thickness of the lamella. And where the moment where you have the most curvature, this is defining the thickness of the lamella. So here it's already less than 40 millimeters. You put the glue inside, you hold it down, and when it's strong, you can slice it. You see it here on the left side. You can slice it like a salami, and then you put it the second time into a jig and you glue it again. So this is like the singly curved beam, and that would be the doubly curved beam. And this explains quite easily the costs you have in producing these beams. So this is how these blanks look like. This is a cross section of these doubly curved glulam. And the different types of beams we have is like straight beams. We can always work with 40 millimeters lamellas. Singly curved beams, there we always still have a lamella, but the thickness of the lamella is dependent on the curvature. And then doubly curved beam, where we work like we slice the lamellas after the first cut and glue them again. So in the end, the section would be like small sticks. Here you see the comparison between the cost versus geometry. And I think this is very important to understand. Like no curvature, you have a price X. And doubly curved wood is between 3 times to 15 times more expensive. And singly curved wood, like these are very rough costs. But what you see is 1 to 50. So if you say you have like 1,000 euros wood or 15,000 euros wood, there's a big impact of costs in a project. It's like 1,500%. Very often we try to save 2% or 3%. And here, if we are not taking care of these parameters, we can easily get the project 1,500% more expensive. So why are we using doubly curved wood and not straight wood? This has to do with the fiber cutting angle. If we have a beam, we have to get the fiber of the wood in the direction of the structure. And here you see a diagram about the strength of a beam of wood according to the direction, the fiber angle. So if you have something, wood is super strong in compression and in tension along the fiber. and wood loses nearly all its strengths, like 90 degrees to the fiber. You can imagine if I have a piece of wood and I pull it along the fiber, or if I push it along the fiber, I can hardly break it. But if I turn it 90 degrees and I take a lamella, it's very easily to break it. So now we have the segmentation, and on the segmentation, we are working with the joints. We work with lots of different kinds of joints, like very traditional wood joints. In the Cambridge Mosque, like this part here, we work with normal lap joints, but also with steel connection, with steel plates, and all kind of connections. But even these small lap joints are quite complicated to generate, because in the end, if you have a lap joint, you always have one direction you can place a segment into another segment. So if you already have here 2 lap joints, the geometry of these joints become quite complex. So at that moment, we got a kind of Lego system, and we have the all the parts of the building, and all we have to do in the production is produce these Lego beams. So in the project of the Cambridge Mosque, we had 30 trees, 145 different types, 2,746 individual beam elements, and they were all produced out of 23 different blanks. The amount, like one tree had 22 kinds of like normal types, but some parts were connected to a glass window, some parts were connected to a wall. So very often these beams were quite similar, but they had some changes and different kinds of connections. So from design to production, we got really this kind of Lego system. Here we have the 23 blanks, and then we on this axis, in the x-axis, on the y-axis, you have all the kind of different types of beams which we needed to produce for the project. So now is the moment, or how do we get from the virtual to the reality? In wood construction, normally you have straight wood, you have like beams, you have panels, and for the beams, you have a Hundecker machine, you have industrial processes which are extremely fast, and it's very difficult to top the performance of this process of cutting on a Hundecker machine. The same applies for CLT and for panels, but when we talk about freeform structures, it's a complete different story, because freeform structures, you cannot produce them in these Hundecker machines because they can only produce sticks or panels, and you don't have a software for it. So the first 3 freeform projects were all built with Mastercam, SurfCam, PEPs, all these kind of CAM systems, which are also used for the automotive industry. The difficulty is, in the automotive industry, you don't care how many hours you use to create a CAM for a certain part, because very often this part afterwards is produced thousands of times for cars. In the wood industry, especially like buildings like the Swatch building we've done, we have very little repetition. And then it's very important to have a software environment where you can parameterize and script it in a way that you are much more efficient. So what we used, rather than using a Cambium for a Hundecker machine or a traditional CAM software, we have produced our own script software from Rhino. So we are scripting in Python, and we are using the geometry from Rhino, and out of the geometry, we are directly generating the G code for the machine and producing it on the machine. So here you see different kinds of beams, how they get into the company. Here you have some singly curved parts. These are doubly curved parts. Here's also singly curved wood. And this is the machine we have in Gooff. It's quite an interesting machine. It's a unique machine on the market. You have, it's 60 meters long, and you have two kinds of machines. You have a machine where the portal is movable, or where you have a fixed portal. We have a fixed portal, and then we are placing the wood on these carriers. It has advantages and disadvantages. One disadvantage is that when you have doubly curved wood on these panels, the wood might be under tension. If you start cutting into the wood, the fibers have spring-back forces, and these spring-back forces are going onto these carriers. And when we have very big beams, there might be so many tensions that we have problems moving the carriers in the machine. A very big advantage of it is that we can place the wood, and we have one aggregate here, one on the other side, and one in the basement. And there we can mill the wood from all the sides without flipping it. And this allows us to produce an extreme precision. Here you have some beams which are just getting out of the machine. Here you see the machine inside. The tools are here, and in the basement you have a second spindle which can process from the bottom. Here you see the wood getting into the machine. This whenever it gets out of the machine, normally you always have defects on the wood, because we work with glue lamp. So sometimes these knots are falling out, or you have a delamination, or you have some parts of the wood where you have a defect, which you don't see as long as the beam is complete. But when you start milling, you might see a kind of defect, like a resin pocket, which is like falling out. And then we have to fix these kinds of defects on the wood. One small thing I want to say is about how we fix the wood. This is another project. It's not the Cambridge Mosque. It was for the Swatch building. Everything you see here is like doubly curved. It looks quite straight, but it's not. It's doubly curved. And the difficulty is, when we place this on the machine, it has to be quite precise on the machine, because we only have like 1 to 2 centimeters on each side to mill the final beam out. So for that Swatch building, we used a kind of system where we were able to fix the wood on the machine. And in our code, we could define exactly where these carriers were standing in X. These things could be moved in Y, and then these posts could be lifted in Z. So each X, Y, Z point was able to be reached. This is how the wood gets into the machine. And here you can see already a little bit of difficulty we have. This is a beam we've done for the Swatch building. You see, we already have a very long tool here. And the tool is already so long that you get a lot of vibrations on the spindle. And it's not long enough. So you see, we cannot cut in until the end, because then we would touch the beam here. So this is where we use the spindle from below and cut the rest from below. And this allows us to make all these kind of very precise pockets in a way where we get the precision which is demanded. Like this, in this beam, we had a precision up to 1.2 millimeters here. There we have like conducts, which are not important for the structure. Here we had a precision, a tolerance of 0.7 millimeters. And in these shear knockets, shear connections, there we had a kind of Kato connector between one level and another one. There we had the engineer asked for precision of 0.1 millimeter, which normally in wood is insane. It's like super difficult to reach. But when you have it on the machine and you don't have to flip it, you can really keep the precision. I showed this placing of the wood with these posts. For the Cambridge Mosque, we started to create a big table because we had a lot of small parts, and it's not very effective to use such a big machine on small parts. So we started to create a table with, I think, 16 parts built at the same time. But in the end, it didn't work out. So even that we are quite experienced with this, we also have to learn on the production, and we have to change strategies. So here we changed the strategies and got rid of this table and produced a different way these parts. Some parts of the Cambridge Mosque are so twisted that we had to go down with the tools and work with a negative angle. And this is why we had to lift them so high, because normally you don't want to lift them so high because you get a lot of vibrations. But here we needed to do it because otherwise we would have had collisions on the tool. So this is how we fix these things first. And then after the first milling, in this case, we flipped them. And then we did the final milling on the other side. So here you see how they are getting out of the machine after the final milling. Normally, when we have to flip a part, we try to do all the connections and all the steel and bolts and whatever we have to do in the project on the first, like on one milling side. And then on the other milling side, we try only to do the kind of one surface, which is only a visible surface, but is not a surface which has to do anything with connections. And this is how these parts are looking afterwards. You can see how they are twisted, and you understand that when you mill it from this side or from that side, there's always one side where you have quite a bad angle. This is why we had to lift these parts so high. And then after milling, we do, this is like in wood, a very common thing to do prefabrication as much as possible. So we do not only take care of all the defects of the wood, but we try to make and assemble and pre-assemble as much as possible on site, whatever we don't have in the factory, so that on site, the whole thing becomes really kind of Lego system where everything fits if we work correctly. Here you can see another part, which this is this kind of doubly curved part, where we also created a kind of jig to produce it. And what you have to understand, I was talking about the spring back forces. If you make a tonnet chair, you can steam the wood and then you can bend it when it's hot, and then you do a compression into the fiber of the wood. And when it's getting cold, you have a little bit of spring back forces, but you can bend the wood extremely, and it stays more or less like this. In our case, we have the wood which is like bent in a cold way and glued together. So if I would like chip and take out all the glue at this moment, this beam would get straight again. So you have to understand that the whole thing is something which is always quite under tension. And you have to take consider this in the production of it. Here you can see also final parts with all the joints, everything we have done, we have put inside. Like very often here you can see 3 holes, and there are a lot of holes. So we have steel plates, which we fix with bolts in the factory. We close these holes later on, so this is still not finished. And then on site, we only have like 3 holes, which are making a steel-steel connection, and then we're closing them on the side. This is the prefabrication of the dome. And when we chip things, like we produce everything in Gossau in Switzerland, and for the Cambridge Mosque, we produced 60 to 80 trucks. So to save money, we try to optimize these trucks. So everything is also drawn in 3D to be sure that we can optimize it on the truck. So this truck is really up to 4 meters, so it goes under the bridges, and it's the maximum length you can have without needing a police car, which is following. We also have this when we have project in Switzerland, but then very fast you get a super expensive logistics by exploding transportation costs. We do not only draw everything which is freeform, we really draw every truck in 3D, and we do not only ship the wood, but we ship also all the tools we need. Like at the moment, we're working with Norman Foster in Saudi Arabia, and we are shipping everything, every screw, every machine, everything which we use, except of cranes and things like this. We ship them from Gossau to the construction site. Another thing you can see here is that everything is foiled. This is very important because the wood, when we get it out of the forest, it has a moisture of over 30%. We dry it to something like 12%. And when the wood is dried, we glue it together with this moisture, and we keep the moisture of 12 plus minus 2% until the assembly of the project. So when we do something like in Cambridge in the UK, you can be quite unlucky with the weather, and you just have to wait until you get a sunny day. And when you have a sunny day, you start assembling your project from 3 in the morning until 3 in the morning, I guess. We try to pre-assemble as much as possible in Gossau. What we cannot pre-assemble in a meaningful way in Gossau, we do a second kind of pre-assembly under a shelter on the site, so that in the end, we have really big parts which are placed into the building. I don't know if you know the freeform structures from Frei Otto of the 60s. There's one beautiful structure in Mannheim called the Multihalle, the Multihall. It's quite interesting because he was able to create all these amazing freeform structures with no computers, no milling, no CNC machine. But he had a complete different strategy. He used very small segments with a thickness of 50 by 50 millimeters. He produced everything flat on the side and pushed it into the place, and then he only fixed the knots. Nowadays, with the technology we have, we use a kind of different philosophy. We create very stiff building parts, very big parts, and here you have something like 40 meters from one point to another one. And we try to stay in tolerances of 1 to 2 millimeters. And we assemble them in a way that we get the assembly at the weakest part of the part from one to the other one, so that when we assemble it, we still have the possibility with a screw from the side to pull the part 1 or 2 millimeters in one or the other direction. So that in the end, when you look at the project, everything is super neat and you don't see any kind of gaps or yeah, that everything is super smooth. Here are a few impressions of the project. This is the dome. I was talking about these 145 types. So here you have beams. You can see that they have different connections to different members. Placement of the dome. That's a view from the inside. This is how I saw the project the last time. And here you have a happy assembly team. So you see the yellow guys are all from Switzerland and the red guys are from the UK. And so we have our staff going on site, and very often, like no one in Switzerland is allowed to use a crane in the UK for the regulations. So we always need together with local craftsmen. And here are final views from the inside. And this is the prayer hall. And one beautiful, I think it's a beautiful idea from Marks Barfield, is they have a ring light here. And this light is projecting the light into the window. There's blue foil on top of the window. And if you're here inside, you always have the impression that you're in an Arabic country with a lot of sun. And when you're getting out of the building, you are, you get in the reality of the English weather back. I'm not presenting the complete project because I want to show a few other things, but just to show another big project we've done in Switzerland. That's the headquarters from Swatch, located in Biel. Biel is a watch city. We have the Jura, a mountain, and the farmers in the mountain, they were very poor people. And in winter, they could not work. So they started the tradition of creating watches. And each of these farmers was specialized in one part of one watch. And then you had these companies which were assembling everything and shipping it all in the world. And Swatch as a company is like in the mecca of this watch city. And you have like Rolex, Tissot, Omega, all these companies are located here. And Watch was buying Omega, and Nicholas Hayek asked Shigeru Ban to make a headquarter for Swatch, and Shigeru Ban did a kind of snake which is biting into this Omega building. It's quite a huge building. It has a length of over 200 meters, a span of over 30 meters, and a height to 25 meters or 26 meters here in the neck of the snake. And it's a complete parametrized building. It's also a building done together with design to production. Design to production entered very early in the game and produced already the geometry for Shigeru Ban. And it's interesting, it's completely parametrized. That means this knot you have here is exactly the same than this one. So it's a grid structure, and you just have one beam which is like turning here and going in this direction, and the other thing goes in this direction. So these balconies you have here are just holes in this kind of structure. So it's 4,600 segments, all doubly curved. There's not a straight surface in the whole building. And the longest structural beam is 135 meters. And you can see the directions, it's always changing. So this was quite a challenge to produce this building. Here are a few final views. So here they call it also the Cobra. So this is the Cobra. This is the conference hall. And this is the tongue of the snake, maybe. We are able to produce very complex things, but we can also produce more simple and more modest things. And I just want to show another, on the other side of the range, a building, kind of public building we've done for a small community in Böttstein. They wanted to create a kind of Tonnendach, cylindrical roof. The architect came and he wanted to have a Zollinger roof. A Zollinger system is a system where a beam is always connecting two, going over two fields, and then you change the direction and you change the direction. And it was invented by an architect, Zollinger, a German architect, who was able to produce these kind of freeform structures with straight beams. It's a super intelligent system. We decided not to do it this way, because when you created Zollinger roof, you need a complete substructure of the whole roof. And they did not have so much money. So we just made one member in the, a temporary member in the middle of the building, and with one very big beam, and then small beams in the other direction. So basically we only have two kinds of beams, a long beam in one direction and short beams in the other direction. If you look carefully, you can see that this one goes through and this one is not going through. But when you enter into the building, you cannot perceive it. But it makes it much easier to produce, much faster, much a much smaller amount of different kind of elements, and in the end, it's much cheaper. And that was the challenge, to produce this building in a very economical way. So the last thing I want to show is a few teaching projects I've done with, before getting to Blumer Lehmann, with the TU Graz, with Blumer Lehmann, and also with the BFH. And what I wanted to show this is this kind of digital change. This has nothing to do with freeform. This is really like straight beams. And here I'm specifically using the technology of Hundecker and Cambium, which is extremely efficient. So I show the project maybe first. The idea was to produce a high seat. I wanted to make a high seat because then it was clear that from a structure point of view, the whole thing had to stand. We did it in Graz, in Austria, and we were sponsored by, that's quite interesting, the University of Graz has nearly no money, like they had 400 euros for the whole semester. And you need to get sponsorships for everything. Like Hundecker gave the software, Chabicha allowed us to use his machine, and Meyer Mellenhof was giving us the wood and the trucks for the transportation. But Meyer Mellenhof is a very rich family in Austria. I think they own 25% of the country, and it's like 25% which is wood. Like all the wood belongs more or less to that company. And they have a lot of deer and they have to hunt them. So they said, okay, we sponsor you, but we would like to use it as a hunting seat, which I was not so fond of, because you have a lot of people who are architects who are not so fond of producing a hunting seat. So in the end, some students wanted to realize the project, and they really tried to make kinds of hunting seats. And then you had a few projects which were complete against hunting, and they tried to create projects where no hunter would like to sit on, or which you could definitely not use as a hunting seat. But they came quite well out. So we worked in the first stage, we worked on connections. Then we left this moment, we produced these kind of stick models, and we did not think about the connection. And afterwards, we tried to combine the knowledge we took on the connection and created meaningful connections here. So in the end, we produced this part out of 56 different kinds of elements, and it was produced on this machine. And what was quite interesting is we never went to this machine first. So we came with the software, with BVX code, on a Monday morning at 7 o'clock, and at 8 o'clock, the first piece came out of the machine. That was to everyone quite amazing. A lot of people thought that we would fail in doing it. And this is like the project as it stands. I've done another project over 2 weeks with the BFH. It's School of Applied Science in Biel, also very connected to wood. And we had a kind of concrete wall, and I asked the student to create a structure spanning from one part to another. I expected them to do a kind of roof structure, or do a kind of like something where you have like normal forces, and they came with this kind of idea. And I said, this is not the most meaningful way to span from one side to another. But we are university, so we are able to fail if you want. So we produced everything not on a Hundecker machine, but on the machine of the BFH, and yeah, it fits. It's also a freeform surface. It's all sticks, and you see the connections here. They are all planar, but it's also a kind of shape which is always between one of these stars to another one, where they connect. There you take the kind of curvature into the beams. It was quite interesting how the students solved this. That's another project we did in the BFH. It's also a project with a combination of sticks and panels, everything with BVX. And the interesting thing here is that we assembled all of these projects in half a day, even less. That was the fastest project I've done. That's 1 kilometer of wood. I gave the students a kind of task doing a round table. It was a group of 46 students. They came from 4 different universities, didn't know each other. They didn't know the topic. And they had to create groups. And each group had to create a structure to hold this kind of table and seat for this round table. So when a big group got a big piece of cake, a smaller one, a smaller piece of cake, and they got 5 hours to design it on a Monday. And then on Tuesday, they had to do a 3D model of it. On Wednesday, we did construction drawings. On Thursday, we produced the wood 1 kilometer on this machine. And on Friday, we assembled everything on site. So here you see the final project assembled on Friday. In Switzerland, when you assemble something, this is something which is amazing at the IAAC, that you can assemble stuff and leave it, and you have students of older semesters seeing what other people have done. In Switzerland, everything has to be cleaned up a few hours after the assembly. And here we had a big chance that a bar, which was located not far away, they said, wow, we like it, can we just take the structure? And they just took the structure over the weekend and reassembled it for them for this kind of pop-up bar they created next to the lake of Bienne. That's another project we've done with BFH. We wanted to promote this kind of digital Abbund, like joinery work on the Hundeker machine. But we worked in the Jura. This is where these watches are produced. And there was a craftsman, carpentry, and they had no CNC machines. And it was sponsored by the Parc Chasseral, and they forced us to use the wood from the region, which is perfect, but also the technology from the region. And we had no CNC technology there. So it was quite interesting after having done all these kind of super digital workshops, to go back on a kind of super manual machine and do all of these joineries like they've been done 100 years ago. We changed them a little bit to make them easier and to be able to assemble and produce everything with the work of the students. This is an image how it looks now. And this we've done for the we couldn't really do it for, the idea was to make a digital hut from Vitruve, like a very typological hut, and then create a kind of structure around in the morning in Zurich, and then go with a truck and visit some wood buildings in Switzerland, and in the afternoon reach Gossau and then produce everything. So the idea was to parameterize out of these kind of lines on the surface, these sticks, create a kind of stick model, take it over into CAD work, where you can generate these joints extremely fast and easy. Then out of these joints, you produce the BVX code. And from the BVX code, you go on the Cambium. This is the tool from Hundeker, from which you can produce it on the machine. You can visualize everything, and you we did it in Gossau. This is our Hundeker machine. We also have one. These are the sticks, and then you get this each of these elements very easily out. And again, it's a Lego system, and you can build this hut in 1 hour. And the last project, I've done it for the University of St. Gall. It's a charrette. It's the first day of the first week of the architectural studies in St. Gall. And there were 84 students, and we created 6 groups. And again, it was a 5 days workshop. So the first day they had to do a hut and a place for 2 people to stay together. So the first day they had to do an analog model for in Balsaholz wood. And on, again, it was first day analog, second day a digital model, third day a construction model. The fourth day we constructed everything, and on the fifth day everything was assembled on site. That's it from my side. Thank you very much for your attention. Wow, I see there are a lot of people listening.
Thank you so much, Kai. Thank you for, I think that this work, it's like a huge celebration of timber, no? From the very small scale of a 5 day or 3 day structure to biggest projects such as the SWAT complex or the Cambridge Mosque, of course. And I really want to thank you because it's a fantastic insight of the work that you're doing. I think that the use of the Cambridge Mosque has been really nice way that you get us through all the processes that you're doing, all the steps that you are working on I mean, from the very small detail of the lamellas, the direction, to the customized scripts that you're using for design optimization, or even to the hacking of the carriers in order to be able to cut wood, and of course even to the optimization or even design of the tracks for the delivery. So I think that it's really nice to see all this work. I also see that all the work that you're doing is a very important reference on the potential of the merge of computer-aided design and computer-aided manufacturing. I think that none of what you're doing would exist if we didn't have CAD or if we didn't have CAM, and the importance that you're giving in both. I think it's really fundamental. Although you're a production, a timber production company, it's clear that it's not possible to do that without having all the computational, let's say, skills and research and all the work that could be done in computation in order to help that. So thank you, beautiful work. I have a lot of things more to say, but I see that there are also like a lot of questions in the chat. So I would like to take the possibility to open the floor, and maybe you all would be nice that you switch on your camera and we have a discussion with Kai. Alejandro, would you like to switch on your camera and ask your question about residual stresses? If not, we can read it in the chat. Okay, I think Alejandro cannot do that, but there is a question in relation to the residual stresses from curving the beams, I guess, the double curved beams. And the question is whether there are any stresses that needs to be accounted for, and how this could be estimated or calculated.
Yes, we take them into account, but we don't calculate them. What we do is normally we try to do all the major cuts in the wood so that we de-stress the wood as much as possible. And that in the end, the last cuts we do are really the cuts which are important for the connections for the next beam, which is connecting. So it's a strategy about what we cut at what time. We had one project in the Netherlands, and there was singly curved beam and a doubly curved beam out of a singly curved blank. And we cut through a lot of lamellas, and there we were always cutting from one side, then on the other side, one side on the other side, to slowly get the piece de-stressed, so that in the end we take the final 5 millimeters, and then we don't have a beam which is moving anymore. So it's more about a strategy, what you cut at what moment, and what you cut at the last moment when you hope that the whole beam is not moving anymore. But we're not calculating it.
Okay. There is a question, there are a series of questions, I think, from Ocean about the future of timber construction, but a lot of the questions are related to the environmental impact of Oscar. Are you here? Do you want to quickly sum this up? Cool.
Yeah, can you hear me okay?
Yeah.
Hello, Kai. Thank you for the lecture. Very, very cool. My question is about the glue that's used to produce the forms. Is there an environmental impact of producing the glue? And then at the end of the building's life cycle, in order to potentially recycle the wood forms, does the presence of the glue impact that process?
If I'm very honest, I have to say yes. It's like we are producing waste which we cannot recycle later on. But on the other side, when I'm looking at this mosque, I hope that it's not going to be building which is going to be recycled or torn down after 30 years or 45 years. So I think as a building, it can stand for hundreds of years. And this is putting in relation of using a material like glue. The glue inside of the wood is about the amount of glue we use is about 2% of the glue. And I know, like the BFH, they are doing studies. What they're trying to do is they try to separate the fiber of the wood and the lignin of the wood, like the internal glue, if you want, of the wood. And they try to recombine it in a beam or use the lignin as a glue. If they are successful with this, then you're able to do a glue lamp, which is 100% natural material. But I think that the freeform structure will never be like, you won't make social houses with freeform structures. So I think the whole industry of wood, or the market of wood, has a lot of different kinds of field. And in Zurich, there's one building where they try to use wood with no glue at all, and they try to process the wood as little as possible. And they promote their building as a bank. So they say they're creating a bank of wood rather than putting money into a bank. They put the wood into the building. And after 100 years, when you do a new construction with new apartments, you can reuse the wood, and it's super dry, and it will be very valuable. So it's like you have wood and you have interests, and it's getting more and more expensive. But in the freeform part, we are using PU wood glue, which is not, we cannot recycle it.
Yeah, that makes sense.
Burn it.
Right. Thank you.
Building as material banks, no? But no double curved freeform.
Not double curved. Yeah.
Okay.
The other quick question, that just to follow up in an environmental sense, there's a lot of transportation of the lumber, the trees to the factory, and then the forms to the construction site. Does it make it less feasible to have timber construction everywhere, especially in regions where maybe there's no forests? Or is it still environmentally positive sum, even with the shipping?
No, it would be much, much better if you'd use local wood and you process it locally. Switzerland is not the cheapest way to produce wood, or the cheapest country to produce wood. So we can only do these kind of flagship buildings because we are able to do something which industry in other countries are still not able to do. The moment where we've done something in Bangkok for Apple, the moment you have an industry in Bangkok which is able doing it, we are out of the game. This is clear. And it's good because it's bullshit to produce something and ship it all around the world. On the other side, I think what we are doing are like these lighthouse or icons of architecture. And I've done a presentation in Poland. And before me, there was a forester of the state, and he gave a very depressive presentation. And he said they have to produce 1,600 constructions in wood in Poland, from a building to a stall. And he said that even the foresters, the people working in the forest, they don't want to build wood buildings because it's supposed to be for poor people and poor buildings. So they wanted to have concrete and stone and so on. And then I did my presentation on the Swatch building, and the first reaction was, hey, this is bullshit. Why do you come to Poland and show us this kind of presentation? And I said, this is exactly what is needed. You need a kind of lighthouse project, maybe in Warsaw, which is promoting the wood. And then you might get other construction done, normal housing, and you get acceptance of the wood. You still have a lot of countries where wood is not accepted. A lot of people find it super interesting to build in wood, but if they construct their own houses, they prefer to have a stone building because it's more solid to their opinion. So I think it's okay under understanding that we are creating these lighthouse projects and that they are promoting wood in countries where wood would not be promoted like this. But maybe this is a marketing argumentation.
Thank you. Thank you, Oscar, for the question, and Kai. Tom, I don't know if you're there. Tom is part of our faculty. He got very inspired. You know him very well. Kai,
I know him very well.
Hi, Kai.
Hi, Tom.
Go ahead.
Good to see you. I just had a quick question, just on the topic of tolerances and production, and it's a very simple one. Just how do you know when you've made what you are making? How do you know that it is what you wanted to make, and how do you quality control your process from a production point of view?
So we get the tolerances from the engineers. They tell us exactly what kind of tolerances we need. And in the Swatch building, I think the tolerances were they were overdoing on tolerances, because when we assembled the Swatch building, we assembled the neck. We had a precision of 0 millimeters on the top of the building, which is insane of wood. And we only got it because we measured every piece which is coming out of the machine, we measure it. Okay. That's one thing. A second thing is wood is still flexible, even if you have thick beams. So you can still somehow pull it a little bit in a direction and get, so whenever you have these 5 millimeters of tolerances, you get 0 millimeter because you can still pull it a little bit to the 0 millimeters. But in the Swatch building, I'm sure that we lost a lot of money because we did so super precise parts. And in the end, the assembly was super quick. And I think with a little bit more tolerances, we would also have been able to erect it, and we would have been much faster in the construction.
Thank you.
You're welcome.
Thank you. Victor has a question in relation to whereas the transportation is also designed or taken into consideration. Victor, are you here? Do you want to say your question?
Yes, sure. Now I wanted to ask how big the role of the transportation is during the design process, since it probably also has a big impact on the costs. And the way, for example, you showed the trucks, it kind of appeared like the form and function of the wooden pieces comes first, and then afterwards you think about, okay, how do we get them to the construction site? Or at least like, it's like it comes last, kind of. Yeah.
Yes and no. The size of the beams, normally, like in the Swatch building, we try to make everything about 12 meters long, because 12 meters is where you can put maximum on a truck. If you would have done the segmentation to 15 meters, we would have got over length trucks, and then it becomes much more expensive to ship from one place to another. So the maximum size to transport something in an affordable way from A to B, this is taken very early in consideration. But once you know that your beams are small and you can put them on a truck, then you're not going to optimize really the truck to 100% to be sure that you can get like 2 beams more on the truck. So there is a moment when you know, okay, I have the segmentation, everything gets on the truck, then you do the project, and when you do the logistics, you think exactly how you are transporting it. And then very often even if we could like save 5 trucks to ship things to Cambridge, we would not do it because the order of erecting is always defining what comes at what moment on the site. Very often we don't have place on the site, and we don't want to leave the wood in the weather conditions. We are not 100% sure. So whenever we have a truck, we know already at the assembly that is the thing erected from the truck. Then we consider the order of how we are loading the truck in Gossau. And this is the reverse order of how we are doing the prefabrication, which is the reverse order again of the production. And we are constantly doing these kind of piles and putting one pile on the next part and so on. So this is a quite complex logistical task, which takes a lot of experience.
Thanks a lot for the answer.
I guess this part of the logistics is pretty interesting, but also crucial in order to save time or to save material, not lose any critical parts because of the non-appropriate way that they arrived on the sites. No.
Mm-hmm.
Okay. There are a couple of more questions. Natalie, are you here? Natalie is basically asking about the software used, whereas Rhino is used for modeling the truck loading, I guess related to logistics again, or what other softwares are being used in general for modeling and for 2D drawing generation, and how the work could be simplified when it comes to better understanding assembly drawings to the people that they're working on site, I guess.
Yeah, so assembly is not a big problem because you have the assembly order which is defined, and very often it's very clear when you have a big beam. It's very clear there's only one way of getting it into the structure. The software we're using is basically Catwork and Rhino. Catwork is the software or the carpenters know. Rhino is something they don't know so much. So when someone is doing designing the logistics of the truck, if I'm doing it, I use Rhino. If they're doing it, they use Catwork. But the freeform stuff, like the modeling of the parts, when there are freeform surfaces, it's 95% done in Rhino. Catwork is also able to work with NURBS nowadays, and they can import the NURBS and take all the attributes out of the Rhino model. The communication between Rhino and Catwork is very good. And the 2D drawings, we use a lot of 2D drawings for the prefabrication of the beams with the steel parts inside, the bolts and the screws, and this is very complex. And there we do 2D drawings. Again, sometimes we draw them, sometimes we script them, sometimes we have design to production doing them. But basically the biggest software we use is Catwork and Rhino.
Okay. There is a last question from the MIPE team from the Valdaura campus of IAAC in Alex, or who is there? Are you there? You want to ask the question? Okay. There is a question of whereas bamboo could have similar potentials to the engineered wood products that you have shown today. So can we do similar things with bamboo, I guess?
Yes and no. Bamboo is super strong. You can do these construction scaffoldings done in bamboo. They use them for high rises. So bamboo is a super strong material with excellent qualities. One big difference between bamboo and fir, what we're using in Switzerland, is that bamboo by itself is a very strong wood in the way it's constructed, but it's hollow. If you want to do a glue lamp in bamboo, you have a lot of manufacturing of cutting the bamboo and gluing it together. But nowadays, there are a lot of people investing in different kinds of wood. But another kind of wood a lot of people are investing at the moment is palm trees, because you have a lot of palm trees for the food industry. And there's not so much things you can do with these palm trees. They're quite difficult to be cut with industrial machines. And I know that these tool makers, they are investing a lot of knowledge and research now in cutting different kinds of trees. And this is like bamboo and palm trees. But yeah, in Switzerland, I think we will not be connected so much to the topic of working with bamboo. A topic which might come to us maybe earlier is not using softwood like pine and fir, but using hardwood like oak and beech. Because of the climate change in the forest, you will have more and more problems to plant softwood in lower altitudes. So at the moment in Europe, there's more shift in going into hardwood for construction and in planting hardwood now. But again, this is something which you will recall in 50 years, 60 years.
Kai, one last question from my side. I really enjoyed the beginning of your presentation, showcasing the diagram that you explained, that you are part of every step of the process, from the extraction from the growing almost of wood to the upcycling of every byproduct that you have within the process. And I wanted to ask you, because we know that the engineered wood processes, glue lamination or CLT, they are all include or require material, wood and timber material, that they're pretty straight, no? And we know that that's not the case of a tree, because the tree has a trunk that is not absolutely straight as we need it. And of course, there are different kind of complexities and differences and diversities and variations of the tree trunks. And I wonder, within this kind of circular thinking that the company is going for, whereas there are other processes that could minimize, let's say, the waste, quote to quote, because it's not waste, it's biomass, I know, and it could be reused, no? Yeah. But the waste of this part of the trunk, and how can we build or adjust our designs to the geometries, that they are much more related to the initial geometries of our raw matter, no?
This is a difficult question to answer, because I think on one side you have an industrial process. So you have a designer who has no knowledge about what trees are really in the forest. And they're designing something, and then you use the wood in a kind of industrial way of 30 millimeters lamellas, which you can bend and you can produce whatever you want. And then the equation becomes quite simple. When you look at how a carpenter was working 100 years ago, they had the wood and they were adjusting the parts of the wood in the construction. And then they had like bent parts of the wood, which they used the potential of the bending part of the wood. You even had a market of not straight wood in Germany and in Europe. Like it was used for ship makings, like this part in the front of the ship, which is like not straight. You could buy it from a wood market which was specialized in using this wood, which is not straight. But from an industrial point of view, you try not to have this wood, because it's so difficult to put it into the whole equation. And at the same time, normally the wood, a trunk is always straight. But when you have inclined landscape, the trunk is always going normal out of the landscape, and then it's growing straight to the sky. So then you get this kind of curvature in the wood. But you have a lot of tension in these parts of the wood. So if you cut these parts straight, you will get a lot of distortion, and so I understand the beauty of using the potential of the wood in these kind of things, but putting this in an industrial equation makes it quite complex.
I see. That's very clear. Thank you very much, Kai. Thank you for sharing the work, your passion for timber, and the different projects that you have shown, both from the company, but also from your different academic endeavors. I hope we can get you very, very soon in Barcelona and see some of the work that we're doing, and help us do some of the work and projects that we're developing. Mm-hmm. Thank you for being generous and be here with us today. And thank you everybody for being here and discuss with Kai.
Thank you very much for the invitation. It was a big audience.
It was
much bigger than in a normal room.
That's true. That's true. Okay. Have a good evening. Thank you, everybody.
Okay. Thank you. Bye. Bye, Areti. Bye, Tom.
Bye. Bye.
Bye.